Hello everyone, so in this section we're going to talk about indefinite integrals and the net change theorem. So indefinite integrals are really just a convenient piece of notation for antiderivatives. And the net change theorem is just a restatement of fundamental theorem of calculus part 2. So we just want to look at these in a slightly different way, and that they'll be useful for some applications. So starting with indefinite integrals, indefinite integral is just this notation, integral of f of x dx. And notice there are no limits a or b or anything else. So it's just the integral of f of x dx with no limits, and it represents the general antiderivative. And we already talked a lot about antiderivatives before we started doing integration. So now we can just reuse all those to calculate all kinds of indefinite integrals. So it's a general antiderivative, so it just means we have to find a function whose derivative is the thing we started with. Okay, for instance, we said that the antiderivative, or the general antiderivative of x to the n, is x to the n plus 1 divided by n plus 1 plus c. Okay, so the indefinite integral of x to the n is just x to the n plus 1 divided by n plus 1 plus c. So these indefinite integrals are just a shorthand for find the general antiderivative. For instance, the antiderivative of cosine x is sine x plus c, so the indefinite integral is sine x plus c. Okay, so every rule we had about antiderivatives can be restated for indefinite integrals like this. So what is the connection? So let's be careful at the different types of integrals we've seen. So we saw the definite integral from a to b, which had limits of integration, a and b. And this represented signed area. So it was a number, not a function, and it was the signed area from a up to b. Whereas now we have the indefinite integral without limits, and that's the general antiderivative. So they both look very similar, so it would be nice if there was a connection between the two. And luckily there is. So how do we calculate the definite integral? Well, as we said using FTC part 2, right, we said to find the definite integral, we should find an antiderivative, plug in a and plug in b and subtract them. And that's exactly what this formula is saying, right? On the left, we have an antiderivative. On the right-hand side, we have the indefinite integral, which is just an antiderivative. And then this piece of notation says plug in b and plug in a and subtract them. So this is the connection between the different types of integrals. But don't be confused if check if you're being asked to find the definite integral, or the indefinite integral. Check if your answer is supposed to be a number or if your answer is supposed to be a function. Right? So indefinite integrals, they are functions that are the antiderivatives. Okay, so let's review all the antiderivatives we've seen so far, using now the notation of indefinite integrals. So we said if we want to find the antiderivative of a constant times f, we just do the constant times the antiderivative. Okay, so we can say the same rule just using indefinite integrals. The indefinite integral of a constant times f is the constant times the indefinite integral. Okay, antiderivative of a sum is the sum of the antiderivatives, and similarly with subtraction. Antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c, if n is not minus 1. If n is minus 1, then we have the integral of 1 over x. Antiderivative of 1 over x is ln absolute value x plus c. So here, be careful. The most general thing to do is to write ln absolute value x. ln x only works if we already know that x is positive. Okay, integral of e to the x is e to the x plus c. Integral of b to the x is b to the x over ln b plus c. And you can pause the video if you need a second to have a look at these. And then they're all the same rules for trig, right? So the antiderivative of sine is minus cosine. Antiderivative of cosine is sine. Antiderivative of secant squared is tangent. Antiderivative of cosecant squared is minus cotangent. Antiderivative of secant times tan is secant. Antiderivative of cosecant times cot is minus cosecant. And by the way, we kind of remember that cosecant and cotangent follow the same rules as secant and tangent, except with this extra minus sign added in, right? So if we go from the third rule to the fourth rule, we swap secant to cosecant, and we switch tangent to cotangent, and we add a minus sign, and we get the rule. And similarly, from going to the secant x tangent x to cosecant x cotangent x, right? We swap them for the evil twins and add that extra minus sign. Okay, antiderivative of 1 over x squared plus 1 is inverse tangent, or arctan x. And the integral of 1 over the square root of 1 minus x squared is inverse sine, or arc sine x. Okay, so we have lots of indefinite integrals that we already know how to calculate using antiderivatives that we talked about. Okay, so next up is the net change theorem. And it's really just a restatement of FTC part 2. Remember, back in that video, we even said that FTC 2 was comparable to this statement. So why are we highlighting it here? Well, we're just going to highlight that there are some useful physical applications of this, or physical interpretations. So here we're saying that the integral from a to b of the derivative is f of b minus f of a. So what do these things represent? Well, if we think of f as representing some physical quantity that's changing in time, then f prime of x is the rate of change, whereas f of b minus f of a is the change over the whole interval. That's called the net change. So we're saying that integrating the rate of change is equal to the net change. So let's see some examples. So for instance, if dn over dt is the rate of population growth, so we say we know how quickly a population is growing in time at any given moment in time, then we can calculate the rate of change over the entire interval, or the net change over the entire interval, just by integrating the rate of change. So integrating the rate of change gives us n of t2 minus n of t1. That's the net change in population from time t1 to time t2. Okay, or for instance, we know the rate dv over dt at which water is flowing into a reservoir. Say we have 100 meters cubed per minute, or 100 milliliters cubed per minute, or something like that. Then if we integrate between two times, we'll get the amount of water, the net change, so the amount of water that's flowing in between times t1 and t2. So integrating the rate of change is equal to the net change, and both the rate of change and the net change are things that we're typically interested in kind of physical problems where things are changing in time. Okay, so moving on, one kind of extra thing that's a little bit special that we should highlight is the difference between displacement and distance. So displacement over an interval is the total amount by which we've moved. But if we move and then go back to where we started, the displacement is 0. So the displacement includes directions. If you go one way and then come back, it's going to count that as 0. Whereas distance counts, if we go there and we come back, it's still a positive distance. So displacement is just the change in position. Distance is how far we actually moved over that interval. Okay, so we know that velocity is the derivative of position. So if we want to integrate our velocity from time t1 to t2, then how do we integrate? We have a definite integral. We look for the antiderivative. The antiderivative is position, and we plug in the different endpoints. So we get s of t2 minus s of t1. So integrating the velocity gives the displacement. That's the change in position, or the net change in position. But if we want to actually find the distance traveled, so if we go somewhere and then we come back to where we started, we're going to say the displacement is 0, but the distance we traveled is definitely not 0. So how would we cope in that case? So in that case, we have we want to get rid of the signs, right? So if we have something that's positive and something that's negative, we want both of them to count. So we don't want any negatives canceling the positives. So in that case, we should integrate the absolute value. So we do the integral from t1 to t2 of the absolute value of the velocity, because we don't want negatives and positive. We don't want one direction and then the other direction to cancel each other out. Okay, so let's see how this works in an example. So how do we integrate these absolute values that look kind of complicated? So let's suppose we have a particle which is moving with velocity v of t, which is t minus 2. How do we find the displacement? How do we find the distance traveled? So the displacement is easy. We just integrate along the entire interval. So we do the interval from 0 to 4 of t minus 2. We find the antiderivative, which is t squared over 2 minus 2t. We plug in 0, we plug in 4. Both of them are going to be 0, so we get 0 in the end. Right, so this makes sense where we're moving in one direction. So when we start, if t is very small, t minus 2 is negative. So this starts moving to the left. And then when t is bigger than 2, this becomes positive. So then it moves to the right. So we move to the left, we move to the right, and in the end, we get back to where we started because it's symmetric. But the distance that's traveled is very much not 0. So how do we calculate that? So we said we should integrate the absolute value of the velocity. So here, the absolute value of t minus 2. And then to get rid of this absolute value, we want to split up according to when the thing inside is positive and when the thing inside is negative. So remember we said that if we know the thing inside the absolute value is positive, we can just get rid of the absolute values. Absolute value means make it positive. So if we order it as positive, we don't have to do anything. Whereas if we know it's negative, then we should swap the sign. We should add a minus sign and get rid of the absolute values. So right now, if we go from 0 to 4 of t minus 2, sometimes it's positive, sometimes it's negative. So we can't use either rule. But if we split it up and we say instead of integrating from 0 to 4, we go from 0 to 2 and then from 2 to 4, then on each of those intervals, we have a separate sign, so we know how to split it up, right? If we go from 0 to 2, it's going to be negative, so we want to swap the signs. Instead of absolute value t minus 2, we have 2 minus t. And if we go from 2 to 4, we know the inside is going to be positive, so t minus 2 is going to be positive, so we can just delete the absolute value. And now we have two standard integrals that we can just do in the usual way, right? We find the antiderivative, 2t minus a half t squared, or a half t squared minus 2t. We plug in 0 and 2, or 2 and 4. We get a different answer in each case, or in this case, 2 plus 2, and we get 4. Okay, so if ever you want to integrate something that has an absolute value in, split the domain of integration according to whether the thing inside the absolute value is positive or negative. Simplify the absolute value separately in each case, and then work out each of those on their own. Okay, so that's about wraps it up for this video. So we said indefinite integrals are integrals that don't have limits on. They're really just a convenient shorthand for antiderivatives. Then we talked about the net change theorem, which says that the integral of the rate of change is the net change, and it's really just a restatement of FDC2. And then at the end, we said if we want to calculate the displacement, we integrate the velocity, but if we want to calculate the speed, we integrate the absolute value of the velocity. And to integrate the absolute value, we should split according to when the thing on the inside is positive or negative. Okay, thanks everyone. See you next time.